All right, Chapter 9, Section 4, the tangent ratio. This is going to be the first of 3 trigonometric ratios that we cover in this chapter. All 3 are actually some that you have seen before, even if you didn't know exactly what they did or what they meant. On your scientific calculators, just to kind of focus in on this, many of you will recognize these 3 buttons. As I called them when I was in high school, sin, cos, and tan. But each of these represents a different trigonometric ratio. Sin stands for sine, cosine for cos, and what we'll cover today, which will be tan for tangent. Right? Each of these actually does something. And if I were to take the sine, cosine, or tangent of a given number, it's going to actually spit out a real number result, with a couple of exceptions that we can go into a little bit later. But for the most part, this is actually the convenient part for this section and section 5, which will be starting with next week early on, is that these operations can actually just be done with the series of button smashes on your calculator. So that's the good news. Okay. Not that there's bad news attached with it. Okay. We will be doing some algebraic kind of gymnastics with trying to move stuff around within an equation to solve for a variable. But beyond that, it's essentially just calculator work. Okay, so again, this is going to focus around the first of the trigonometric ratios, and this is a direct reference back to the title of our unit. So to remind you, right triangles and trigonometry. Trigonometry being the science of right triangles, essentially, like the ratios and the relationships between the sides, the angles, the whole 9 yards with right triangles specifically. Okay, so here's the formalized definition of a trigonometric ratio. It is a ratio of the lengths of 2 of the sides of a right triangle. So there's a key operative right there in the end, and it's the fact that we're only dealing with right triangles. This is kind of important moving forward because what trigonometry is essentially going to do is it's going to marry together the relationship between an angle measurement, how far apart 2 side lengths are from each other, what we would measure as a degree of angle measurement. And it's going to relate that angle measurement to the lengths of the sides of a triangle, which are seemingly 2 completely separate measurements. Okay, degree measurements, or how wide an angle measure is, how wide a wedge is that creates an angle, and then the length of the sides of a triangle have different measurements entirely. One's in degrees, one is in units of length. Okay, and what we're finding is that we can relate these together. And there's actually a simple reason why that ties into a previous section. Okay, and this is going to go back to AA theorem. AA theorem, to remind you, had to do with similarity. This is a chapter 8 concept. And it dealt with the fact that any 2 triangles that had 2 angles that were congruent to 2 other angles meant that the 2 triangles were similar and therefore would have a scale factor between the 2. So why is that being applied here? Because since we're dealing only with right triangles, one of those angles will always have to be the same. And that's the fact that all right triangles have at least one angle measurement in common. Their 90-degree angle. And what we're going to start dealing with trigonometry, with relating an angle measurement to the lengths of its sides, what we're going to require to use trigonometry is we want to relate an angle measurement to 2 other sides on this triangle. And so fundamentally, I'm going to need to know an angle. So let's say I know this angle right here. And if it's going to be the same as, say, this angle here, I have just met the requirements for AA theorem. And here's what I'm getting to. How trigonometry is used. Let's say in a right triangle, for whatever reason, I know that this angle measurement is 32 degrees. We'll actually deal with an example that uses that exact degree measurement. But let's say I know this one's 32 degrees. Then no matter if the triangle is smaller than this guy or bigger than this guy like this, if that angle measurement is 32 degrees, I'm going to be able to build a relationship with the lengths of the sides. Okay, and using AA theorem, whatever that relationship or ratio between 2 of the sides needs to match the other ones because they are similar to each other. They're scale models of each other. So if this side right here is half the length of the hypotenuse, then this side right here would also have to be half the length of its hypotenuse. Even though they would have larger numbers, that ratio would have to be the same. And so because of that, specifically with right triangles and only having to lock in a single other angle measure, we're going to be using the AA theorem as the justification for why we have these ratios to begin with. Okay, so that may have been a little over your head as far as where it comes from and why it gets the reasoning behind what it does. So let's just start jumping into what we're actually going to be using. Okay, so to start with, the tangent ratio. Actually, before I get into the tangent ratio, let me talk about what's over here in the margin. There is going to be a very helpful acronym. I'll scroll it down here because I want to make it big and bold on the top up here. There's going to be a very helpful acronym that we're going to be using for these next couple sections dealing with trigonometric ratios. And that acronym is going to be SO, CA, and maybe you guys have heard of these before, SOHCAHTOA. Okay, SOHCAHTOA. Now this sounds like one of the campgrounds that we have up here in Big Bear and stuff, but what this is essentially breaking down is a relationship for our trigonometry. This is not too much different than like PEMDAS that you use for order of operations. Okay, it just kind of gives us an idea of what's related to what. And we're going to be focusing on the TOA today. So the S, C, and T are going to refer to a specific trigonometric ratio. S is for sine or the sin button on your calculator. C is for cosine or the cos button on your calculator. T is for the tan button on your calculator, the namesake of our section today being the tangent ratio. The O's, H's, and A's are going to refer to basically what two sides we're going to be relating to each other in a given right triangle. Okay, and as I said before with that little illustration at the beginning, was that if I know one of the angles, whether it's angle B down here or angle A up here, since I'm dealing with right triangles, there will always be some other angle that is similar to another in another triangle, and that if I know a given angle measurement, there will be a constant ratio between the sides. And those ratios are expressed by the sine, cosine, and tangent. Okay, so let's talk about the OA part of TOA. I've written over here in the margin, but for tangent, it's going to be associated with opposite over adjacent. Opposite over adjacent. So this is going to end up being the punchline for today's section, opposite over adjacent. But what does that refer to? Okay, fundamentally, sine, cosine, and tangent are going to be applied to an angle measurement. Okay. When I use the sin, cos, tan buttons on my calculator, I'm applying it to a specific degree measurement. Okay, so for instance, if I knew angle B was 32 degrees, I could take the tangent of 32 degrees and it's going to spit out some crazy decimal. What that crazy decimal is representing is the ratio of the side opposite and the side adjacent to that angle. So if I took the tangent of a different angle, like say angle A, again, I would take the tangent of whatever degree measurement was on the inside right here, and it's going to tell me the relationship between the lengths of the side opposite that angle A and the side that's adjacent or next to it. Okay, so first off, if it actually helps you over here in the margin, you can describe what adjacent means if you didn't already know. Adjacent literally means next to or sharing a border with. For instance, California is adjacent to the Pacific Ocean. California is adjacent to Mexico. California is adjacent to Nevada, but California is not adjacent to Hawaii because it doesn't share a border with it. Okay, so for adjacent, what I would talk about, say like, again, taking the tangent of angle A up here, opposite over adjacent, I would look at the length of the side opposite angle A, whatever length this was, however many units that was, however large or small. And then I would put that in a fraction form over the adjacent length. Now you may be thinking like, all right, well, angle A has two sides that are next to it or adjacent, you might argue, but this side is given its own special name. Okay, this side, the one that's opposite the 90-degree angle, is what we would call hypotenuse. one that we're very familiar with now, not only throughout this unit, but you should already have been familiar with it from years past. The hypotenuse of a right triangle is always the side, the longest side that's opposite the 90-degree angle, the largest of the three angles. And you'll see that when we get into sine and cosine next week, that h is going to represent hypotenuse for that length. So when I'm talking about opposite and adjacent sides, we're talking about opposite and adjacent legs, to be a little bit more specific. So if I'm talking about the tangent of angle A here, I would take the length of the leg opposite, BC down here, and put it over the length of the adjacent leg, the leg that's next to angle A, which would be AC right here. Okay, so kind of seeing this in a little bit more longer written out way right here, the tangent of some angle A, again, whatever angle measurement is there, and there is an actual specific degree measurement there. But if I were to take the tangent of that degree measurement, okay, it would spit out the ratio between the length of the leg opposite, BC, over AC, the length of the leg next to it or adjacent to it. Opposite over adjacent. Now, if I took a tangent of a different angle, like say angle B, then that ratio, it's still opposite over adjacent. It's just the lengths of the sides may differ depending on what's going on in the triangle. Okay, so for instance, if I were now taking the tangent of angle B, and angle B will have a different degree measurement, okay, unless it's an isosceles 45, 45, 90 triangle, in which case they'll both be the same. But in either case, I'll focus here for angle B. And again, I'm going to look at what length of the side is opposite. In this case, it'd be AC, whatever AC would end up measuring. And then that would go over whatever is adjacent to or next to angle B down here, BC. Okay, so this is simply going to break down as tangent of some angle, where these will be some angles. You'll never really take the tangent of the right angle. We never do a trigonometric ratio of the right angle. It doesn't really give us enough information, and it kind of breaks down at that point. We're only going to be talking about the other two angles of the triangle. Okay. And so in this case, the tangent of some angle is going to be the leg opposite over the leg adjacent as far as length goes. Okay, well, let's see this in example form, because this will probably be the most simplest way to understand what is being talked about right here. All right, so we're going to do 3 examples. They'll all be really quick. The actual computation here is going to end up being pretty straightforward. Okay, so your first several problems will look like this. You'll be given a right triangle, and you're going to be told the lengths of all 3 sides of that triangle. You could even, if you were so motivated, test it out using Pythagorean theorem. There is no need to that. There's no need to confirm whether or not this is a right triangle like in section 1. But suffice it to say, 18 squared plus 80 squared will equal 82 squared. Okay, so we have a right triangle here. That's not what's being tested. In this problem, we are being asked the following. Find the tangent of angle S and the tangent of angle R. Okay, so I'm going to look for 2 different results here. I'm going to write each answer as a fraction and then as a decimal rounded to 4 places. I have all the information I need right here. This is essentially just going to break down into reducing a fraction. So let me jump to the whiteboard so we can see this a little more clearly. All right, so in this problem, we are given the following. We're given this very long, narrow right triangle. Triangle RST, and it is a right triangle. So we have this right angle down here at angle T. And then we're given all 3 side lengths. S to T is the short side. That's going to be 18 units long. R to T down here is the next largest at 80 units long, a big jump there. And then the hypotenuse, which should be the longest of the 3 because it's opposite the largest angle, is 82 units long. So that all tracks. And if I was so motivated, I could do 18 squared plus 80 squared should equal 82 squared. But again, that's not what's being tested here. I'm being asked about the tangent of 2 different angles. Okay, so the first thing I'm asked about here is the tangent of angle S. So the first thing to do here would be to identify angle S. Simple enough, it's up there. Now, I notice I don't have an actual degree measurement here, and that's okay. Okay. In other instances, it might tell me like, all right, this is how many degrees this angle is. This is going to be on the larger end of the spectrum. compared to how small this guy will be. This 90-degree angle will still be the largest, but this one's going to be pretty big too. Okay, so if I was given an actual degree measurement, I would actually be able to take the tangent of whatever that degree measurement would be. It would spit out some decimal on my calculator. As it's kind of given to me, I don't know what angle measurement that is, so there's no way to actually plug this into my calculator. However, whatever the tangent of an angle is does equal this ratio, opposite over adjacent in a fraction form. Now, opposite what, adjacent what? In this case, I'm talking about what's opposite angle S and what's adjacent to angle S. And for this, it's just basically looking at what I got. So in this diagram, what side length is opposite angle S? Well, there's angle S. Opposite would be this 80. So 80 degrees, or sorry, not 80 degrees, 80 units. It's a length, okay? 80 units long is what's opposite the angle S. That's going to be put over whatever's adjacent or next to angle S. Again, I wouldn't choose this 82. This is the hypotenuse of the triangle. That's given its own designation. We'll deal with this guy on Monday and Tuesday. But again, what's adjacent is this 18. For tangent, I'm dealing with the legs of a right triangle, opposite and adjacent. Okay, so this ends up being the tangent of angle S. Last thing I would just simply do here would be to reduce the fraction. 2 goes into top and bottom. It would reduce to 40 over 9. It doesn't go any further beyond that. So this is the fully reduced tangent of angle S. Okay, it also asks me to put it into decimal form, rounded to 4 places. For that, I would simply plug that into a calculator. This is a division problem ultimately, so I'll just do 40 divided by 9, and that spits out this long 4 repeating decimal. So simplifying that, that would be, or rounding that, that would be 4.4444 repeating, but rounded, it gets to this for the 4 decimal places. Okay, so what does this result mean? Okay, for the record, we've answered it, but what does it actually mean? So this is a ratio between lengths of sides. Whatever angle measurement exists here, okay, so let's say, for instance, it's like, I don't know, 75 degrees. Okay, I don't know for the fact what angle measurement is. But whatever angle measurement existed here, it's telling me how much bigger or longer this side is compared to what's adjacent to it. In this case, this side opposite that angle is over 4, it's 4.44444 times bigger than that. If I were to take 18 and multiply it by that number, it would give me 80. Okay, it's relating the lengths of these two sides based on what angle measurement this is. And that's important because if I had the same angle measurement on, say, different numbers, okay, maybe it was a much smaller version, so smaller numbers, or a much bigger version and had massive numbers, as long as that angle measurement is the same, this ratio would end up breaking down exactly the same. No matter how big these numbers got or how small these numbers got, that ratio would still break down in the same way. Okay, so the other part of this question told me to look into angle R. Let's just do that really quickly. So then I'm tasked with finding the tangent of angle R. Again, I do not actually have an angle measurement in this case. So my ratio is still the same, opposite over adjacent. Opposite what, adjacent what? In this case, now I'm focusing on angle R. And now in this case, I'm going to focus on angle R. Now the side that's opposite is going to be this 18 and adjacent is going to be the 80. So really it's just going to take the reciprocal of this fraction. Let's just kind of finish that out. So in this case, it's going to end up as 18 over 80. That would reduce with 2 going on top and bottom to give me a 9 over 40. And this is actually going to be the signature of the trigonometric ratios, is that if I swap the angle, I'm going to end up with the reciprocal essentially. Okay, and so if I were to do this on a calculator, because again, it told me to do it to decimal places, I would do 9 divided by 40, gives me this decimal. So again, that's going to break down the relationship, in this case, 0.2250 technically to 4 decimal places, but there's the equivalent in, or the approximation in decimal form. And what does this tell me? This tells me the relationship between these two sides. It's a much smaller angle. Okay, it's a much smaller angle in this diagram. So whatever angle measurement this one ended up being, this ratio down here that we just solved for tells me how much smaller this guy is compared to the ones next to it. Okay. All right, let's move on. So this next example is actually going to be a little bit more of a practical usage of the tangent ratio of trigonometry in general. And I'll describe why. Okay, so this next example says this. We're given the following diagram, and we're asked to solve for x, essentially. So this is going to be the most common way that you see these trigonometric problems. You're going to be seeing right triangles like this with, they'll tell you a degree measurement, and they'll give you some combination of two of the sides, usually telling you the explicit length of one of the sides, and you have to solve for the other one. Or maybe they tell you two lengths of sides, and you have to solve for the angle measurement. Okay, that tends to be the combination, but it's this kind of combination of information in a diagram. And our job here is to solve for x and round to the nearest tenth. So let me jump back to the whiteboard and let's see why we have to do what we do. So again, we're given a right triangle. No labeled points or anything like that, but it's a right triangle. And then we're told that this leg over here is 11 units long, and then we're asked to solve for the length of this one. Okay, so as it's drawn up, you should notice that it's impossible to solve this with Pythagorean theorem right now, at least to get an explicit answer. In order to use Pythagorean theorem, the a squared plus b squared equals c squared, I'd have to know the length of the other side so that I could use, to solve for the one missing piece. As it's given, I'm only given one piece and I need to solve for the other. This is where trigonometry comes into play, okay? Because now I can have less information and still solve for the missing piece. But the other piece of information I'm given here is that this is a 32-degree angle. So kind of like I talked about at the very, very beginning, the very intro to this section, any other triangle, regardless of how large or small this number is, or however large or small this unknown will end up being, this 32-degree angle and this 90-degree right angle, any other right triangle that has this combination will have to have the same ratio of sides. Why? Because this will be similar or scale model version of every other triangle, every other right triangle that has a 32-degree angle. As such, these have to be scale models of each other. That's where we get that relationship. But the spoiler alert here is that I'm going to be using tangent. Okay, not that that's a huge leap because that's the very name of this section. So what I'm going to be using, I can't use Pythagorean theorem because I don't have enough information about the hypotenuse here. So I'm going to have to use tangent, where I'm going to be taking tangent of an angle and then relating it to the sides opposite and adjacent to it. TOA. Tangent is opposite over adjacent. So in this case, I actually do know an angle measurement. I'm going to be taking the tangent of 32 degrees. And for the record, this is something that can actually be done in a calculator. It would spit out a very ugly decimal. Let me just show you really quickly. On my calculator, I have to put in the degree measurement first. In yours, it might allow you to put in like the tangent first, and then it'll be like parentheses, put in the number. But in mine, I have to start with the 32 degrees, and then I would push this tan button, and it spits out this very ugly decimal. What does this decimal mean? Okay, what this decimal is doing is it's relating the length of the side opposite that 32 degrees compared to what will be next to it. So what this decimal is telling me is it's telling me a ratio. Okay, it's 0.6. Whatever this length is here is 0.6 of what this will be. What does that tell me? That this will end up being longer. Okay, this is like a scale factor k. K is less than 1. That tells me that this leg right here is going to be longer than this guy. So anyway, back to like what the problem's actually doing. Tangent of some angle, in this case, the 32 degrees that I'm given, is going to be equal to a relationship. The side opposite that 32 degrees over whatever's adjacent to that 32 degrees. So this is a little bit different scenario than what we had in the last problem. In the last problem, I knew both of these guys, and this was the one I didn't know. In this problem, I know what the degree measurement is. I'm not going to know one of these ones. In fact, this is the one I'm not going to know. But when I plug in these values, all right, the side that's opposite the 32 degrees is this 11 unit length. So that's going to be my numerator. And it's going to be over the side that's adjacent to the 32 degrees or next to it. This is my unknown. So that's where x is going to go. Okay, so fundamentally, my equation here is going to be tangent of 32 degrees is equal to 11 over x. Tangent of 32 degrees is equal to 11 over x. Here's where we're going to be doing a little bit of algebraic gymnastics. Okay, so let me rewrite this a little more condensed. Tangent of 32 degrees is equal to 11 over x, the length of this leg opposite over the length of the leg adjacent, the piece I'm solving for here. Fundamentally, I want to solve for x. That's what the question is asking for. And that's pretty much what these trigonometry problems will be asking for. Like, there'll be some element of these three that I'm having to solve for. In this case, it's this guy. Meaning, I want to get this one by itself. So here's where we're going to use some traditional algebraic moves. Okay. The problem here is that my unknown, my variable, is in the denominator of this fraction. So the first thing I want to do is get it out from the denominator by multiplying it to the other side. So if I multiply x to both sides, I'm going to end up with the tangent of 32 degrees, which again is some decimal. That's an actual number. And that's going to be multiplied by the x I'm moving out from the denominator over here. And now I'm just going to be left with the 11 on the other side. Okay, well, I still want to get x by itself. So now I want to move this mess right here. And it's being multiplied by the x. So the way I'm going to move this tangent of 32 degrees is by division. So in this case, x is going to equal that 11 divided by whatever the tangent of 32 degrees is. And as I showed you on the calculator, it's going to spit out a really ugly decimal, but it's still something that can be done on the calculator, which is nice and convenient. So we've officially solved for x. X is by itself. So whatever this turns out to be will end up being the length of that leg of my triangle. Okay. So let's figure out how to do this in a calculator. First off, many of us would be the simplest thing to do here would be first to do this trigonometric thing in your calculator, take the tangent of 32 degrees, it gives you an ugly decimal, and then just do 11 divided by that result. Because my calculator is especially dumb, I have to do it in the proper order. So I'm actually going to start with 11 divided by, okay, so I'm telling the calculator to divide 11 by whatever I'm about to put in right now. Now, my calculator will allow me to do this in the next operation. Some of your calculators, you have to do this part first and then kind of round that number and then do 11 divided by whatever you rounded it to. I'll let you kind of play around with that. But now I'm going to divide by the tangent of 32. So I have to put in the degrees first and then hit this tangent button. There's the tangent of 32. But remember, I already told the calculator to divide 11 by this number. So now when I hit equals, there's 17.6. So x here, rounded to the nearest tenth, is approximately 17.6 units. All right, so it may have been confusing how I described how to do this on a calculator, so let me do it another way where many of you would just do the trigonometric ratio first. So I would take the tangent of 32 degrees. There's that ugly decimal. Okay, maybe I'll just kind of remember this value and replace tangent of 32 with it. So 0.625-ish. So 11 divided by 0.625. That's just the rounded version, tangent of 32, gives me 17.6. Okay, so the one trick with that is if you ever round this trigonometric ratio before you do this kind of stuff, you'll notice that this is slightly different than what result I got before, even though I ended up with the same rounded result. If you're ever off by a tenth or two or something like that, it's probably because you rounded one before you could have. In any case, we find out that the side length is 17.6 units. Let's just do a little sanity check back here at the original diagram. And let me just point out that using the triangle sum theorem in this triangle, if this one's 32 degrees and this one's 90 degrees, the fact that all three have to add up to 180 is going to force this guy here to be 58 degrees. And so the fact that this angle is larger than this 32 means that this side length should be longer than the 11. And so the fact that I got 17.6 tracks with that result. Cool. So that's an actual application of trigonometry right there. All right, one more example. This one will be brief. It's a little bit more conceptual than anything. It's down here at the bottom. Use special right triangles to find the tangent of 60 degrees. This is actually a direct reference to section 2 notes on special right triangles. So let me just briefly describe what's happening there. This comes from 9.2 on special right triangles. And the special right triangles that were covered in that one, there were 2 of them. There was the 45, 45, 90, the isosceles right triangle, and then there was the 30, 60, 90. Both of these refer to angle measurements, where 45, 45, 90 refers to the fact that I have a right triangle who has congruent legs. And then the 30, 60, 90 was a little bit more of a stretched out version. Again, right triangle, but I have a smaller angle and a larger angle. All 3 still follow the triangle sum theorem, where all 3 angles have to add up to 180 degrees. That was covered in section 2 notes. But the other punchline for why these 2 are special kind of has to do with trigonometry. The fact that because these triangles will be similar to all other triangles that have these angle measurements, there ends up being this common ratio between the sides. So for a 45, 45, 90 triangle, you get this 1 to radical 2 ratio. What that means is if this is 10 units long here, this would also have to be 10 units long. That's why it's isosceles. But if I want to find out the length of the hypotenuse, I take that 10 unit long length and multiply it by whatever the square root of 2 is to find out the length of the hypotenuse. The 30, 60, 90 triangle had its own set of ratios, where the shortest leg opposite the smallest angle, the 30, we'll call that a 1. Whatever length this was, I would double it to find the length of the hypotenuse. And this was the weird one. The one opposite the 60 degree angle was this radical 3, or square root of 3. So for instance, if this was 10 units in length, just like in the last one, this one would be 10 times 2 units length, or 20 units long. And then if I want to find this length, I would take that 10 units and multiply it by the square root of 3. Okay, so again, that's just a quick review of what happened in section 2. And so in this problem, this example, it says, use special right triangles to find the tangent of 60 degrees. So essentially it's like, all right, well, what's the tangent of 60 degrees? And why would I use special right triangles? Well, let me point out that there is no 60 degree angle over here, so this one's just not helpful. But there is a 60 degree angle here. And so I'm going to use this special right triangle to figure out what the tangent of 60 degrees is. It's actually just what we did. The tangent of 60 degrees is still going to have to be opposite over adjacent, opposite whatever is 60 degrees, and then whatever adjacent to 60 degrees. It's just that now I'm using these 3 ratios for those values. And so what is opposite the 60 degrees here? That radical 3. So for my ratio, the tangent of 60 degrees is the square root of 3 over whatever's adjacent to or next to this 60 degree angle, which is this side length of 1. And so what's the tangent of 60 degrees? Is this radical 3 over 1, which anything over 1 just equals itself. So what's the tangent of 60 degrees? Square root of 3. That ratio is always going to take place. So let me prove that on this calculator. So for the record, I can actually take the tangent of 60 degrees by putting in my 60 and hitting that tan button. Crazy decimal. But let's think about it for a second. 1.732, yada, 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 yada. So keep that in the back of your mind. But I've just established that whatever the tangent of 60 degrees is, whatever that decimal was, has to match whatever the square root of 3 is. So if I actually just do the square root of 3, notice I get the same exact decimal. This tells me the ratio of whatever's opposite 60 degrees, this square root of 3, divided by whatever's adjacent to the 60 degrees, which is this 1. So that's just how to relate it back to section 2 with special right triangles. It's essentially the same exact thing with what we're talking about now with the tangent ratio and what we'll talk about Monday, Tuesday with the sine cosine ratios. It's just that we're not locked into just this combination or this combination of angle measurements. It can literally be any angle measurement. This is just more of a very, very specifically applied one. But that'll go ahead and conclude our notes on section 4, the tangent ratio. I'll go ahead and stop recording there.